Welcome back. This is the part 2 of the SmartSort design. If you missed the part 1, here is the story in one breath. We have designed a SmartSort machine and we have already designed its mechanical and electrical part under the standards, international standards. So right now the machine stands completely lifeless. No motion, no logic. A body without a nerve system. In the next few minutes, we'll change that. We turn electrical energy into the controlled torque. We give the machine a disciplined, standards built brain, and then we go to the part that separates engineering from hope. We prove with arithmetic and with law the smart sort is safe and legal to sell. So let's pick up exactly where we left off. Layer 3 of the smart sort is basically the handshake between two words. The exact point where digital commands becomes the physical torque. The illustration shows a complete motion axis of the cell. The servo drives, the motor it powers, the encoder on the motor shafts reporting back, and then these dotted line in the blue is basically the information flow, our first cyber signal inside the machine. And if you remember one line from this slide, it should be the drive is the translator between the cyber and physical world. So the stage 1, motion specification under IEC 60034. For each smart sort axis, we define the torque, speed, duty cycle, and match load inertia to the motor inertia. These are very important because an undersized motor is not a performance issue, it is the safety problem just waiting for the hot afternoon. Stage number 2, motor and drive sizing. IEC 60034 standard duty type and the thermal classes mean continuous duty at this torque says exactly the same thing to the motor makes in Japan and the motor builds in Lahore. We add overload margins, handle the braking energy to the servo throwback. Then the stage number 3, and this is where it gets genuinely clever. The safety function lives inside the drive. Under IEC 61800, safe torques of remove the power that create torques electronically without dropping the main supply. We will safely torque off the system. So the system 1 bring the axis to the controlled stop first, then apply the stop after. Safely limited speed lets a technician jog smart sort robot slowly, guard open during setup. Each function carries a certified SIL capacity and capability. Safety engineered into the drive. Note bolded beside it. Stage number 4, the actuators and the pneumatics. Under ISO 40414, pressure relief, soft start valve, and defined safe behavior when air is lost. So the gripper never become a projectile. Stage number 5, the emergency stop under ISO 13850 with IEC 60947 devices. The, the red latches mechanically and it contracts are basically direct opening. The physical art of pressing force that apart, and basically here is the deepest safety principle in that talk. The circuit is hardwired, completely independent of the software. The last line of defense must never depend on the very computer it is protected you against. Stage 6, commissioning under ISO 13855. We measure SmartSort's actual stopping time with instruments, then compute the minimum safe distance using the standard hand speed constant. That measured number, physics, not opinion, dictates exactly how far the hazard, the light curtain is mounted. So now everything physical exists and is energized, all of it waiting for one thing, a brain. Layer 4 of SmartSort, the brain. And I'll be honest with you, this is my own layer. Look at the illustration. That is the SmartSort's HMI, the operator's window into everything we have built. 1200 items and all, the run state, the safety status showing the PLD, the network health, all served by the PLC and the safety controller you will see on the left over the Profinet. Every pixel of that machine is the output of 6 stages on this slide. Stage number 1. Before any codes exist, we allocate safety requirement under IEC 61508 and IEC 62061. Every SmartSort safety function gets a target. The guard moving the emergency stop and the chain that are basically assigned SIL2 performance level D, derived from the risk assessment, not picked from the air. Remember IEC 61508, it is the parent standard and it ties the next slide together. Stage number 2, architecture, and it should be under the 3 of IEC 61508. Safety code is separated from the standard code. Watchdogs supervise the processor. Diagnostics supervise the sensors. The design assumes things that will fail and define exactly with what SmartSort does when they do. Gracefully degradation is designed, not hopes for. Then the stage 3, implementation. The PLC logic is written in the standardized IEC 61131 language. Ladder, function blocks, structured text, portable and reviewable. Not one engineer's private logic, or you can say private language. The embedded C on the safety controllers follows the MISRA. No dynamic memory inside the safety loop, restricted pointers, no undefined behavior, and no surprises. Stage number 4, my favorite, static analysis and the unit test. Tool checks every line against the code before it ever run. And IEC 61508 scales the required test coverage with the SIL. The more safety you claim, the more thoroughly you exercise your branch. We prove SmartSort software on the bench where a defect cost something like minutes, not on the machine which it costs, you can say, a lot. Then the stage 5, security, under IEC 62443. SmartSort's network is divided into zones and other devices. The firmware is signed, the controllers and the basically firmware the firmware is designed and the controllers hardened. Hold that thought. It gets its own slides in a moment. So now the security, and it is the one that has genuinely changed the profession in the last few years. Let me put it bluntly. A safety function that can be switched off over the network is not safe. It is liability with a certificate attached, and the world has already watched malwares cross from the network into the physical machinery. This threat stops being theoretically years ago. IEC 62443 is the playbook for preventing it, and the logic is very beautiful and simple. First, crave the system into zones of equal trust: the enterprise network, the industrial DMZ, and the control zone and the safety zone. Second, let those zones talk only through tightly controlled network. Every arrow of this diagram is a decision, a firewall rule, a protocol allowed on purpose. Third, assign each zone a security level matched to the threat it must resist. From a casual mistake up to a skilled, motivated attacker. Look at the diagram. The safety zone is the most isolated of all. This is by design, not by accident. And then notice what defense in depth really means. No signal wall is trusted. An attacker who pushes their way into the enterprise network still face the DMZ. Past the DMZ, the control zone, past that a safety zone that accepts almost nothing at all. Here it where it connects to the law of the next slide, the machinery regulation safety, that is basically a safety function that can be treated remotely as a safely defect. Full stop. This is the single sentence is why a modern engineer can no longer hand security off to IT department. So we build it, we have secured it, now we have to prove it's legal to sell. So this slides answer the blunt question every manager eventually asks. So what? Why did we do all of it? The answer is the chain in front of you. 5 steps. Every layer we build feeds into it. Step 1, the risk assessment. That is basically the ISO 12100 document from the mechanical layer. Step 2, apply the harmonized standard. And here is the legal magic. A harmonized standard carries a presumed of conformity. Meaning, if you followed it, the law presumes you met the essential requirements. Step 3, compile a technical report. And then the step 4, sign the EU Declaration of Conformity, a legal document with a named accountable signatory, and only then step 5, the CE mark, not a sticker, a legal passport to the entire market. In plain terms, the law has finally caught up with the cyber physical system. So, moving to the next slide where we will conclude our discussion. Let me leave you with 4 things. One, a cyber physical system is co-designed across every layer. You cannot bolt the physical and the digital world together afterwards and simply hope. Step 2, standard apply from very first requirement, not on the final inspection. Third one, functional safety and the cyber security are not subsystem you can hand to one machine. They are threads that run vertically through absolutely everything. And the fourth, the payoff is conformity. A CE marked, legal, scalable, genuinely trustable system with a technical file that can defend it for decades. So let me end where I began. The standard are the one that holds the system together and makes the person trustworthy, make the person trust on it, and that is why people trust the brakes of their car, the autopilot on a plane, and the pump on a ventilator, because everything is designed under these proper steps. Every layer has every standard inside it. Thank you. I'll be glad to take your question.